Can you guess what a dilation does? What happens when you dilate your eyes? Or contracts. So this is going to be definition 3.21. And can I give you an upshot here? Some of you said you have sat into other linear algebra classes, right? Looking at you, my friend. You remember the 3 elementary row operations? Multiply one row by a scalar added to another row, that's called a shear matrix. Multiply one row by a constant, that's called a dilation matrix. Flip rows, that's called a permutation matrix. We'll do that, right? But this is done right. Yeah, I said it. So we define the n by n dilation matrix. This gets you into the research. The stuff that most linear algebra classes do gets you into 1930s. What do we call this when we add to a matrix an outer product? Rank 1 update. So this is now a definition. Can you guess what we're going to do with this definition? Example. We'll do the one in the notes, and then I think I'm going to let you do the ones for yourself, because this was really beautiful. I gave you 2 full examples, right? That's almost like undergraduate. C is a scalar, yeah, sorry about that. Yeah, C is just some scalar, just like before. So let's do an example, and we'll call this example 3.4.5, and we'll say let n be equal to 5, and consider d sub 2. Oh, I guess I do too many 5s. Sorry about that. Oh, you want to do 4? Okay, I'll mess with you. All right, let's do this then. Let's do -3. And then the thing I'm going to have you do, always, 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 when we're working on these type of problems, what do I specifically want you to do? Not only write the dimensions, but also make specific reference to the original notation, right? So what's J in this case? J is 2. What's C? -3. What's N? 4. Okay, let's go ahead and write the specific notation, or the general notation. So this is the dilation matrix whose jth diagonal entry is C. That's one way to say that. What is the definition of that? I sub n plus C minus 1 times EJ transpose. Okay, let's go ahead and fill all that in. What is I sub n in this case? I sub 4 plus -3 minus 1, and don't you dare actually write -3 minus 1 as a number. Just leave it like that, and you'll see why I do that in a second. How about this one? E sub 2, E sub 2 transpose. What is this dot right there? Really depends on how you associate them, doesn't it? You could say it's a scalar vector multiplication, or you could say it's a scalar matrix multiplication. Could you guess which one we're going to use in this case? Scalar matrix, because we're getting our head around what these things are, right? Let's go ahead and write it down. What does I4 look like? Please don't be so specific. That's a 4 by 4. All right, now let's go -3 minus 1. What does E2 look like? Okay, what does this thing look like? This is a 4 by 1. That's a 1 by 4. So now I've got the matrix 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, plus minus 3, which was my C, minus 1. What's this matrix look like? Yeah, so remember, it depends on, do you all prefer columns or rows? For me, it depends on what I'm doing. Sometimes I prefer rows, sometimes I prefer columns. I really respect Sam, and Sam says columns, so I'm going to like columns, right? So here we go. The first column, I'm going to take this matrix or this vector and multiply by what? 0. So what's the first column of that thing? 0. The second column of the outer product, I'm literally going to take this vector and multiply by 1. So now I get a copy of this vector in column 1 with no scalar, right? In column 2, sorry about that. So now this is 0, 1, 0, 0. And then what's the rest? 0, 0. Yeah, all zeros, which is kind of nice, right? Now I want to do something that is going to look obscene, but it's going to give you access to why we have the C minus 1 rather than just C. So you're going to get intuition on where that minus 1 comes from. I need you to go back to the 8 algebraic properties of matrix arithmetic, or vector arithmetic generalized to matrices. Do you remember what happens if I have a matrix, or excuse me, pretend this was a vector and this was the sum of scalars? Do you remember what we can do on that? Distribute. And that is also that theorem that we didn't write, but we said that we understood. What can I do here? Can distribute. So now I have what? So this whole thing, this implies, using that property, this implies d2 of -3 was going to be my identity matrix. It doesn't really take that long to write all this down. How long did that take me? It took me longer to talk about it than it did to actually write it down, right? So -3 times, what's this? Someone time me on this. I think I can do this in under a second. What does the -1 right there do? What do we know about matrix addition and the order that you do it? Yeah, it's called an abelian group, right? I can move this over to the other side, doesn't matter. This negative right there hits that thing, what does it turn into? It turns into a negative, so now this is 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, plus 1, 0, 0, excuse me, 0, -1, 0, 0, 0, 0, 0, 0, 0, 0, 0, 0. What's left over? 0, -3, 0, 0. And the -3 is in the exact location of the -1. What do you notice here? What happens right there? Now I have a matrix that looks the identity matrix, except what? I'm missing the space. But that space is filled in with whatever scalar value was on the inside there. Right? Pretty beautiful, isn't it? This is not, sadly I did not make up this particular theory. This comes from Piziak and Odell. It's a kind of beautiful book that's underread in this field, in my opinion. Now what happens? Imagine if I had $1 for every entry I wrote today. I'd have like $3 at least, right? You're not funny, Anderson. You're hilarious. Ah! All right. Okay, should we do something? Should we test our powers of imagination? Give me an n that's bigger than 4 but less than 10. 9. No, my God. Oh, I was hoping you wouldn't go there. All right, that's cool. You wanted me to have 81 bucks? All right, so here we go. What if I ask you this? You want to try again?
6.
N equals 6. Okay, that's much better. I just saw Katya look at her watch. All right, so give me a j that's between 1 and 6. 1. Give me another one. Okay, 1. That's cool. All right, and then give me a c.
5.
5. Okay. Without doing all this work, can you intuit, can you tell me without thinking about it what that matrix would be? Okay, use the terminology of lesson 8. This is going to be a diagonal matrix. What is a diagonal matrix? What's the statement about diagonal matrices? Only the main diagonal entries can be non-zero, which means that the strictly upper triangular must be 0 entries. The strictly lower triangular must be 0 entries. In this case, all the main diagonal entries are non-zero, yeah, or equal to 1, except for the entry in location 1, 1, which in this case would be equal to 5. Do you think I'm satisfied with this? No. What would I say if you're training yourself? Yeah. So that's now a challenge for you. Confirm for yourself, using the actual algebra of matrices, like all this stuff, that this matrix is indeed this one. Right? Oh, I just didn't finish. No, I'm just kidding. Yeah, so what is this one? Oh, I'm missing. Oops. This one, right? Yeah. If you just shut your mouth long enough to think, Anderson, you would have seen that.